sheet number 3, questions 5 and 6 that we had for homework last night. 5 says a 92-kilogram football player running at 6.5 meters per second to the north collides with another player to the south. I want to pull out the red pen here already. What do I want to circle? Or if you pulled out the highlighter or whatever it is that you do to draw attention, Finn, what do I want to circle here? Yeah, the north and the south here, right? The more conscious we are of drawing attention to things, the more likely we are to do this correctly. I'll be honest with you. Part of it is like seeing it circled, but part of it is the habit of looking for what to circle, right? Does that make sense? The habit of looking for what to circle or highlight or draw attention to is largely what leads us to not missing that on test day and not forgetting to put a negative in there on test day. The 92-kilogram football player continues moving at a velocity of 2 meters per second after the collision. What's the velocity of the 85-kilogram football player after the collision? Let's number these football players 1 and 2. You could make it the other way around. It wouldn't be a big deal. Doesn't really matter, but this is the way that I've got them numbered, simply because the 92-kilogram football player appears first in the question. Let's write down some givens here now. We're going to say M1 is 92.0 kilograms and M2 is 85.0 kilograms. I always write those down without asking because those are the easy ones, right? The masses are easy. What's next? Something is 6.5 meters per second, 6.50 meters per second. What is that? V what? V1 or V2? V1, yeah, it's V1. The 92-kilogram football player is moving at 6.5. That's V1. Is that V1I or V1F? That's V1I. Good. The initial velocity of the football player. The 85-kilogram football player running at 6 to the south. We're going to make that negative. I'm not going to forget that because I circled it in red. That's going to be velocity as well. Is that going to be V1 or V2, Colleen? V2. Good. V2I. The initial velocity of object number 2. The 92-kilogram football player, what player is that, number 1 or 2? Number 1, the way that I defined 1 and 2, that's number 1. He continues to move at, it actually doesn't say he, it just says the 92-kilogram football player. Could be a she. Okay. The 92-kilogram female football player continues moving at a velocity of 2.00 meters per second after the collision. We're going to say that is V1F, the final velocity. And what's the velocity of object number 2 or person number 2 after the collision? That's going to be V2F. We could analyze this using impulse, but if we did, we'd have to make sure that we picked one football player or the other. We wouldn't want to do them both at the same time. It's object number 1 or object number 2, separately from one another. I'm going to analyze the system here, and if I analyze the system, then I know that momentum is conserved. In other words, total initial equals the total final of all of the objects. Alex? Yep. Yeah, if it continues moving, yeah, probably should have said that, right? Probably should have specified that, but yeah, it would be, it's meant to be continue moving in the same direction. Okay. Is this the one? No, I don't think it is. Never mind. How many objects do we have before the collision takes place? Right, how many we got? Right, so we're going to have two terms, M1 V1I plus M2 V2I. How many objects do we got? Hunter, how many objects do we got after the collision takes place? 2. So let's have two terms again. M1 V1F plus M2 V2 final. Okay, some of the questions that we did, I think 1 to 3, all involved the objects sticking together. So it was M1 V1I plus M2 V2I equals M total times VF. It's not really much different, right? The strategy that we follow is exactly the same. We just ask ourselves, same questions even, how many objects do we have? It's just the answer to that question is a little bit different here. We have 2 objects afterwards instead of 1. Masses cancel. I think the example we did, the masses canceled, didn't they? How come they canceled in the example but not here? Yep. Yeah, same masses in each term cancel, different masses don't. I got 92 here times V1I, which is 6.5. plus m2, which is 85 times v2I, negative 6. Don't forget the negative there. Not likely to, since we got it circled there. M1 is 92 again, times V1F is 2, plus V2, sorry, plus M2, which is 85, times V2F. Calculator is not working this morning. All right. So we calculate this number. We get it. We calculate this number. We add it. Really, we're adding it, but it's adding a negative number, right? So it's the same thing as subtracting it, right? So combine those two numbers. And then take 92 times 2, which is 184, over by subtraction, right? So these two get combined, and then this guy goes over by subtraction, and then we divide by 85. When we do that, we should get a value of 1.13 meters per second to the south, or negative 1.13. Does that make sense? How many people got 1.13? I can't remember who it was that asked me to do question number 5, but is it okay?
Yeah.
Was it you?
Yeah.
Okay. Okay, fair enough. Really, I would say the biggest mistake that people make in a question like this is the signs, the positive and the negative. Okay? The second biggest mistake is you just mess up on a given. Okay? Like if you get those givens correct, it sets you up nicely for this question. And then if you get the signs correct, really at that point it's almost a math thing, right? The only mistake you can make almost is a math thing. Okay, let's see number 6. 75-kilogram man standing at rest on ice, holding a 4-kilogram ball. Man throws the ball at a velocity of 3.5. What's his resulting velocity? Right now, we can predict kind of what it's going to be. Not exactly, but man and the ball. Man throws the ball. Ball goes one way. Man goes the other way, right? Now, is the man going to go faster or slower or the same speed as the ball? Same speed? Should be the same speed, shouldn't it? Because if the man applies a force on the ball applies an equal and opposite force on the man. Shouldn't the man go at the same speed then? No, it is the same force, right? Equal and opposite force, but that force has a different effect on the man than it has on the ball. The man is heavier than the ball, right? So the same force has a lesser effect on the man than it has on the ball. Does that make sense? The man has more inertia, right? More mass. It's harder to change his motion than it is to change the motion of the ball. So he's going to be going slower than 3.5. I don't know how much slower than 3.5, but we know it's going to be slower. Let's number these. Let's make the man number 1, and let's make the ball number 2. M1 is 75.0, and I'm going to make M2 4.0 kilograms. Some velocity is 3.50 meters per second. What would that be? The man throws the ball at 3.5 meters per second. The man throws the ball. Is the ball object 1 or 2? We define it as object 2. So this would be V2 then, right? Is that V2I or V2F? Beginning of the problem or after the event has taken place? What is it? Somebody said it? Paige? Yeah, it's going to be final, right? After or final, V2F. Good? Is there anything else we have? Oh, we're looking for V1F, right? We're looking for the final velocity of the man, object number 1, V1F. There is something else that we have here if we read between the lines a little bit. Amy? Yeah. We're going to say VI is 0. And I'm glad you said VI is 0 meters per second. You could have said V1I, because it is. The man is at rest, but so is the ball. And rather than saying V1 and V2, let's just say VI. Okay? It's one object, right? If they were separate from one another, like if the ball was over here and the man was over here and they were both at rest, I'd probably keep those velocities separate even though they were the same. But since the man and the ball are one, the man is one with the ball, then we're just going to make it VI equals 0. All right, we could analyze the impulse experienced by the ball, or we can analyze the impulse experienced by the man, which, by the way, would be equal and opposite, right? But if we analyze the system, there is no change or impulse. We know that the total momentum is conserved. How many objects do we have before the collision takes place here? How many is it? One. And what's the momentum of that one object before the explosion takes place? 0, right? We could call this m total times vi equals, but man, if it's 0, like if everything's at rest, why don't we just put a 0 in there? Right? Why don't we save ourselves the bother of writing that equation in there? How many objects, Evan, do we have after this explosion takes place? 2, good. So we're going to have 2 terms then, right? M1 V1 F plus M2 V2 F. Can we cancel the masses out here? No. If it was the same mass, could we cancel it out even though it's a 0 on the left-hand side? Yeah, usually we say it has to be in every term, right? But if you get a 0 in one term, it's like it's not even there. So yeah, you could still cancel out there even if it's not on the left side, as long as it's 0 on the left side. I can't do that here though. M1 is 75 times V1F is, that's what we're looking for. M2 is 4.0 times V2F is 3.50. 4 times 3.5 is 14. Take that to the other side by subtracting. Negative 14 divided by 75 is negative 0.187. Should it have worked out to be negative? Yes. The ball goes positive. The man goes negative. Is 0.187 a reasonable number? The ball went forward at 3.5. The man went backward at a lot less. Why? Because the man is, heavier. Yeah, the man's a lot heavier, right? A lot less velocity because of his much greater mass. Let's do one more example. This is example number 4, and this relates to, if you took a look at your Physics 30 and 13 pages document, this relates to physics principle number 15H. Call it a progressive collision. A progressive collision is kind of like a domino effect collision. You can imagine what I'm talking about, right? Hopefully you've never been in one, but you can imagine what happens, right? When you go to a stop sign and somebody is ahead of you and you stop, and then somebody pulls up behind you and hits you, and they propel you forward into the person ahead of you. So car number 3 hits car number 2, and then car number 2 hits car number 1. I call that a progressive collision. A couple collisions are taking place, right? One causes another, and then sometimes causes another, and I mean, you can keep going on and on and on, right? The idea is the same, though. It's a domino effect collision, a progressive collision. That's exactly what we have going on in example number 4 here. It says a 1,000 kilogram car traveling north collides with a 1,200 kilogram car. They entangle. They travel north, and then they hit another 1,200 kilogram car. Now all 3 cars entangle. What's the velocity of the wreckage immediately after the second collision? How do you want to tackle this? How do you want to do this? We get 2 collisions going on. What's the most logical way to do this? Yep. Do it in 2 parts, right? You could say PI equals PF for the first collision, and then you could say PI equals PF for the second collision, right? Is that okay? Absolutely, that's okay. Absolutely. That will 100% work. But if you think about this for a second, right? First collision, PI is equal to PF. And then in the second collision, PI is equal to PF. but you recognize that the PF for the first collision is the same as PI for the second collision, right? Then can't we just say this equals this? In a progressive collision, we don't worry about what happens in the middle. We care about, as long as we have an isolated system, we care about the initial momentum and the final momentum. Like, think about that. The law of conservation of momentum says the total initial momentum equals the total final momentum. I don't care what happens in between. If we make our system big enough to account for everything that's taken place, what matters in between doesn't matter. The initial momentum must equal the final momentum. So that's the way I'm going to tackle this. You could absolutely do it this way. It's just a little bit more work, that's all. If what I'm about to do confuses you, then do it that way. Do it as two collisions. I'm just pointing out that you don't need to, that's all. Alex? Yeah, no, that's a good point. The danger of that is that there could be, friction or something acting in there. Assuming that there are no external forces like friction or so on, this absolutely works. Okay. Depending upon how close these cars are, that may or may not be a realistic assumption, though. That's a good point. Okay, so let's write down some givens here. Let's call this guy number 1, this guy number 2, and this guy number 3. Let's say M1 is 1,000 kilograms. I'm going to say M2 is 1,200, and M3 is also 1,200. Something is 10 meters per second here. That's a velocity, right? 1,000 kilogram car traveling north collides with a stationary 1,200 kilogram car at 10 meters per second. What would that be? Would that be V1, V2, or V3? What is it? Good. That's V1. Is it V1I or V1F in? Good, V1I. What would V2I be? Yeah, that second car is initially at rest. What about V3I? It actually doesn't specify here. Should have said that was a third stationary car. What would V3I be? What would V3I be? 0, good. Okay, now remember, we're looking at initial and final, right? Not in the middle when the middle collision is going on, but like at the very, very end. Oh, look, they stick together. We're just looking for VF, right? All three of them together. Let's say PI is equal to PF. Again, you could do impulse for this, pick a car. It'd be tougher for this because there's two collisions taking place, but you could do it. But let's just analyze the system. The total initial momentum is equal to M1 V1I plus 0 plus 0. You could write in M2 V2I plus M3 V3I, but both of those last two terms are 0, right? Equals mass total times VF. Mass 1 is 1,000 kilograms. Times V1I is 10. Mass total is 3,400 kilograms. You're going to expect VF to be bigger or smaller than V1I. Smaller. All of the momentum was due to one object. Now that same amount of final momentum is now spread amongst 3 objects. So if you have the same momentum, but now 3 objects, more mass, your velocity is going to be less. I'm going to guess here, like the mass is not exactly 3 times the mass, but it's almost, right? So I'm going to guess the velocity is going to be about a third, right? 10 times 1,000 divided by 3,400 gives me a final velocity of, look at that, I didn't open up to my little answer key here. Look for it here. What is it? Oh, I don't even have that one there. 2.94, thank you guys. 2.94 meters per second. So it was about a third, right? the mass is more than 3 times, the velocity is going to be a little bit less than a third the velocity. Is that okay? Okay, like what you said before, you know, right? Like do it as 2 collisions. Absolutely, there's a danger in that, right? The more work you do, the more chance you have of making a mistake. But if you do the work right, that's gonna work. It's gonna work, and it's gonna get you the exact same answer. So, listen, I'd say for one of these questions, just whatever you're more comfortable with. Treat it as 2 collisions or treat it as 1. If you're comfortable with this is less work. If you're not, do it the other way because it's right. Good.